Good evening, sir.
Good evening. Yeah. Is my audio clear to you?
Yes, sir.
Okay. Thank you so much.
Sir, you can start, sir.
Yes, ma'am. Good evening, students. So today we are going to continue with our discussion on current electricity, and first of all, I would like to discuss the concept of temperature dependence of resistance. Okay. So this is the first concept which we are going to discuss now. So effect of temperature on resistance. That is the first concept. Effect of temperature on resistance. So what is mean by effect of temperature on resistance? Because while discussing the Ohm's law, I told you that the Ohm's law is applicable only in case of the physical conditions remaining constant. That means the temperature also should remain constant. Only then the Ohm's law is applicable. So that means when the temperature changes, there will be changes on the resistance value of a conductor. So whenever there is a change in temperature, how the resistance of that conductor varies. Okay, that concept is very, very important. For that, we need a parameter called temperature coefficient of resistance. So this is temperature coefficient of resistance. So this parameter is very important while discussing the temperature dependence of resistance. So temperature coefficient of resistance. So this temperature coefficient of resistance is represented by the letter alpha. Okay. So what is meant by the temperature coefficient of resistance? It is actually increase in resistance value increase in resistance value for every degree rise in temperature. Okay, for every degree rise in temperature, for a rise of 1 degree Celsius temperature. That means initially if you have a conductor and the temperature of the conductor is 37 degrees Celsius. Now when you increase the temperature of that conductor to 38 degrees Celsius, then what is the increase in resistance value? So that quantity is called the temperature coefficient of resistance, that is called alpha. And using this alpha value, you can calculate the resistance of a conductor at any temperature. Okay, at any temperature you can use the alpha value and you can find out the resistance value. So let me consider that I am going to find out the resistance of a conductor at particular temperature T, that is represented as R suffix T, that is represented by R0 into 1 plus alpha into T. Okay, here RT is the resistance at particular temperature T degree Celsius. Okay, so this is RT is nothing but resistance of the conductor at T degree Celsius, and R0 is nothing but the resistance at 0 degree Celsius. Okay, and alpha is the temperature coefficient of resistance, and T is your temperature for which the resistance has to be calculated. So T is the temperature at which resistance should be calculated. Okay, temperature at which resistance to be calculated. So this is the formula for finding out the resistance of a conductor at any temperature T. Okay, when you know the resistance of that conductor at 0 degree Celsius, you can find out. And how will you calculate the alpha value? Okay, so that alpha value, when you don't know the alpha value, what you can do actually, so you can use this relation alpha equal to RT minus R0 whole divided by 1 plus alpha into T. Okay, so from this equation you can derive this equation alpha. That is 1 plus R naught into T actually. So this is RT minus R0 divided by R naught into T. Okay, this is R naught into T. R naught into T. So this is how you need to find out the alpha value or the temperature coefficient of resistance. So similarly, you can find out the resistivity also using the similar kind of relation, that is rho suffix T equal to rho 0 within the bracket 1 plus alpha into delta T. Delta T is nothing but the change in temperature. So rho suffix T equal to rho 0 into 1 plus alpha into delta T. Delta T is actually the change in temperature. So using this relation, you can find out the resistivity also for a conductor at any temperature. Okay. So now, if you find out the alpha value, you can tell how the resistance changes with the increase in temperature. If your alpha is positive, okay. If your alpha value is positive, that means your resistance increases with increase in temperature. On the other hand, if your alpha is negative, okay, if your alpha is negative, then the resistance of the conductor decreases with the increase in temperature. So this is how you need to understand the properties of alpha. So alpha value is negative for a particular set of materials called thermistors. Okay, so that thing you need to understand, and this is all you need to know about the effect of temperature on resistance and also resistivity. Okay. So then we have to discuss something about EMF. Okay, EMF or the electromotive force. The EMF or the electromotive force. So for that, I am going to open the first page. So electromotive force or EMF. So the short form is EMF. Can anyone tell me what is the meaning of this EMF or electromotive force? Can anyone tell me? Yes, students, EMF or electromotive force, can anyone tell me what is the meaning of this?
So,
Yeah, tell me.
so it can be defined as the work done to carry a few amount of charge around the entire circuit.
Sorry, can you repeat that?
Sir, it can be defined as the amount of work required to carry few amount of charge around the entire circuit.
Okay. Any other answers? Any other answers, students? You can unmute yourself and you can talk, no issues. Okay. Actually, EMF is nothing but the energy required to drive the electrons in a circuit. Okay. So the energy required to drive the electrons in a circuit. So that is called EMF. So to be more precise, actually the energy supplied by a cell. Okay, cell. What is meant by cell? It is it is a device actually used to convert chemical energy to electrical energy. Okay, chemical energy to device to convert chemical energy to electrical energy, that is called a cell. So in a circuit, actually a cell supplies the energy to drive the electrons. Okay, so that energy or the work done, okay, to move a unit charge around the complete circuit is called EMF, and it is represented by the symbol epsilon, that is equal to W by Q. W by Q means W is the total work done, okay? The total work done to move the charges, and Q is the total charge. Total charge that is moving in the circuit. And when you divide the total work done by the total charge, you will be getting the work done to move a unit charge. So that work done to move the unit charge around the complete circuit is called EMF. Okay. So SI unit of EMF is actually voltage or volt. So SI unit is volt, and this EMF actually depends on the nature of electrolytes and also the metal of electrodes. Okay, actually in a cell, what is there? Actually, you have electrodes and electrolytes. These are the components of a cell. Okay. So this is what EMF is all about. And the next thing which you need to know is the internal resistance. Okay. The internal resistance. So in current electricity, whenever we talk about internal resistance, we should use a small letter R. Okay. Why we are using the small letter R is that many of the times we actually use the terms called external resistance. Okay. For the external resistance, we actually use the capital letter R. So for denoting the internal resistance, we have to use a different notation. For that, we are actually using the small letter R for denoting the internal resistance. And can you say anything about the internal resistance, students? Can you say anything about the internal resistance?
So,
yes, tell me.
Sir, it is the resistance offered internally by the cell to the current flowing in the circuit, sir.
Yeah, absolutely right. So as I have told you already, inside the cell you are having electrolyte. Okay, the electrolyte offers some resistance. Okay, the electrolyte actually offers some resistance to the flow of electrons. So that resistance inside the cell, okay, inside the cell you will be having a small amount of resistance, that resistance to the flow of electrons. So that resistance inside the cell is called internal resistance. Okay. So that is called internal resistance, and this internal resistance causes some loss of energy actually. Okay, because if you have a particular value of EMF for a cell, okay, the cell won't be able to deliver the complete EMF mentioned in the cell actually. So for example, in certain cells it is mentioned that the EMF is actually 1.5 volt, but when you take a multimeter and measure the EMF of the cell, you won't be finding that it is supplying 1.5 volt. It is always less than 1.5 volt, because the internal resistance within the cell actually causes some loss of energy. So the cell may not be able to supply the EMF value as it is mentioned in the cell. So there is always some loss of energy due to the internal resistance. Okay. So This is what you need to know about the EMF and internal resistance. Okay. So now we are going to discuss about the terminal potential difference. So we are going to discuss the terminal potential difference. So what is mean by terminal potential difference? Okay. So for that I am going to draw a circuit now. Consider that you have a circuit like this. And in the circuit you have an external resistance, okay, that is capital R, okay. External resistance as capital R, and you have a cell here. You have a cell here, and inside the cell there is a internal resistance. So this is small r. The cell can supply an EMF E, okay. And since it is the positive potential here, the current flow is in this direction, okay, I. So now the cell supplies the EMF E, okay, and due to the EMF, there is a current flow in this circuit, okay. Now, what is the potential difference across this resistance capital R, okay? What is the potential difference across this resistance capital R? So, in the absence of this internal resistance, the potential difference across this capital R is exactly equal to the EMF of the cell, okay? In the absence of internal resistance. So, in the absence of internal resistance of the cell, the potential difference is actually equal to the EMF of the cell. But as I have told you already, the cell may not be able to supply the same EMF that is mentioned in the cell, because the internal resistance present inside the cell actually leads to loss of energy. So in the presence of internal resistance, what happens? So in the presence of internal resistance, what happens here? Here this V is actually equal to epsilon minus I into small r, okay. That is, this I into r means the potential energy that is lost inside the cell, okay. So actually using Ohm's law we can calculate the potential difference V equal to IR. Here inside the cell, the potential which is lost is actually I into small r. Due to the presence of this internal resistance small r, this amount of energy is lost, okay. This amount of energy is lost. So V is not exactly equal to epsilon, but minus I into small r. So this amount of energy is actually lost, okay. So here when the cell supplies this EMF, what we have to say is actually the cell is discharging. Discharging means the cell is continuously supplying the EMF to the circuit. That means the cell is actually discharging. So here since the cell is discharging, the potential difference obtained is always lesser than the EMF by an amount I into small r. Okay, so here the cell is discharging and you won't get the exact EMF value supplied by the cell. There is a loss of energy in the form of I into small r. There is a loss of potential actually. Okay, so now we are going to discuss some cases. Okay, we are going to discuss some cases of this circuit and some important points to be understood, okay, for solving the numerical problems. So there are some cases, and that cases we are going to discuss now. During discharging, okay, during discharging of this cell, that means the internal resistance of this cell is included now. So during discharging, what happens? So the current given by the cell I is equal to EMF divided by capital R plus small r. Okay, because you have this capital R and small r in series, so the total current is given by epsilon by capital R plus small r, because the cell is discharging now and you have to include both the resistances. Now the potential difference across the resistance, okay, potential difference across this resistance is given by V. This is equal to I into capital R. Okay, V equal to I into capital R is the potential difference across this resistance capital R. So across R you are having V equal to IR. And inside the cell, okay, inside the cell, what is the loss in energy actually? Inside the cell it is I into small r is the potential, okay. So that makes the EMF of the cell E equal to V plus I into small r, okay. So according to this formula, E equal to V plus IR. So here the internal resistance of the cell can be calculated by this formula, R equal to epsilon by V minus 1 into capital R. Okay, so this is how you need to understand the formula and equations in case of discharging of the cell. Now the second condition is actually the open circuit. Okay, the second condition is the open circuit. So what is mean by open circuit? Can anyone tell me what is mean by open circuit?
Sir,
yes, tell me.
sir, circuit in which there is no current flowing, sir.
There is no source of EMF in the circuit, that is called open circuit. Okay, so there is no source of EMF, that means that is a open circuit. Of course you have the external resistance, but you don't have the source of EMF. That means that cell is not included. Okay, even though the cell is included, you open the circuit somewhere. Okay, let me draw this open circuit here. So here you have the two terminals open. Okay, A, so this terminal B, and here you have the external resistance. This is point P, C, this is point D, and external resistance capital D. And here of course you have the cell of EMF E, but here you have this open. Okay, I think you can understand this. So here, okay, the circuit is open. Okay, so circuit is open, that means even though the cell is there, there is no flow of current. Okay, there is no flow of current. So this is the case of open circuit. This is the case of open circuit. So this is the case of open circuit. So now what happens in case of open circuit? Your current is 0 and the potential difference across VAB. Okay, across VAB is nothing but epsilon. So the cell is open, so V is actually, so in general, the formula is V equal to E minus IR. So since the current is 0 here, we actually get V equal to I. Okay, V equal to I. So this is what happens in case of open circuit. Okay. Now the next condition we are going to describe is the short circuit. So the short circuit we are going to discuss now. So short circuit is nothing but the external resistance is absent here. That is called a short circuit. Here you have just the cell alone. Okay. You have just the cell alone. So here you have the cell alone of EM of E, and you don't have any external resistance here. So the external resistance R equal to 0. This is called short circuit. So short circuit means there is no potential drop in the external resistance. So the current, short circuit current is given by epsilon divided by small r. Okay. So here you see I equal to E by capital R plus small r. So during short circuit, this capital R becomes 0. So the current is given by current equal to epsilon by small r. Okay. Moreover, the potential difference V equal to epsilon minus I into small r usually. This potential difference is now 0 actually. Okay. Because the potential difference is actually the difference in potential across the external resistance. So since there is no external resistance here, there is no drop also. Okay. There is no drop also. So this potential difference is actually equal to 0. So V equal to actually 0. So this V equal to 0. Okay. So these are the points you should keep in mind while solving the numerical problems. In numerical problems, they may give you the scenario of a short circuit or open circuit. Okay. So like that. So in that cases, you need to substitute the formulas correctly. Do you all understand the concept, students? Anyone have any doubt?
No, sir, no doubt, sir.
Okay. So now the next concept which we are going to discuss now is resistors in series and parallel. Okay. Resistors in series and parallel. So resistors in series means it's very simple. Okay. You have this kind of arrangement. So let me draw here an example for resistors in series. So here I am having resistances. Okay. So here it is R1 and this is R2. This is R3 and you have a connection here, source, okay, and the current flows like this. So I have resistors connected in series. This is the series combination of resistances. That means head to tail arrangement, okay. The tail of this resistance is connected to the head of this resistance. So like that, the resistances are connected. In this way, you can have n number of resistors connected in series. So in this case, what is the total resistance of this circuit? Okay, of this combination. So that is represented as R suffix S, that is equal to R1 plus R2 plus R3. Okay. So when the resistors are connected like this, head to tail arrangement, what you have to do is you have to simply go for summation of all the resistance values and obtain the total resistance. Okay. This is how you need to find out the total resistance value. So in the series combination of resistance, the current remains the same. Okay, current is same across all the resistances. Okay, across all the resistors, the current is same. So this is the concept of resistors in series. Okay, and then the next concept is resistors in parallel. Okay, resistors in parallel. So resistors in parallel means it is the stacking of resistances actually. So here you have a battery connection. Okay. So here you have the battery connection, and here you will be having resistances. So this is R1, this is R2, this is R3. Okay. In this way, you can have n number of resistances. So how will you calculate the net resistance of this circuit? That is 1 by R suffix P. Okay. R suffix P is the resistors in parallel combination total resistance. So 1 by R1 plus 1 by R2 plus 1 by R3. So like this, you need to find out the total resistance value. Okay. So for the resistors in parallel combination, you have to apply this kind of formula. Do you all understand this concept, students? Do you all understand this concept? Anyone having any doubts here?
No, sir.
Yeah. Okay. So now we will be discussing one numerical problem. So now we will be discussing one numerical problem. So the equivalent resistance between A and B for the mesh shown in the figure is. They have given you a diagram actually. So based on that diagram, they have asked you this question. So let me draw that diagram here. So here I have a 4 ohm resistance. Let me draw it again. This is almost like a triangle, okay? Here I am having a 4 ohm resistance. That is 4 ohm. And here also I am having a 4 ohm resistance. And here I am having a 8 ohm resistance. Here a 6 ohm resistance. And here I am having an 8 ohm resistance. So here I am having the point A and here I am having the point B. Okay. So this is the mesh or the network. We have to find out the equivalent resistance between A and B for the mesh shown in the figure. Okay. So for this kind of problems, what we have to do is, so before that I'm giving you the options. So here option A is 7.2 ohm. Option B is 16 ohm. Option C is 30 ohm. Option D, it is 4.8 ohm. So these are the options. So for these kind of problems, what we have to do is we have to first draw the equivalent circuit. Okay. So here this circuit may look little bit messy. Okay. So for that you have to first simplify this circuit. Okay, by redrawing it. So how you can redraw this circuit? Okay. So let me show you here. So here you have this 4 ohm and 8 ohm in series, and this 6 ohm in parallel. Okay, so this 4 ohm, 4 ohm, 8 ohm and 8 ohm all are in series, and this 6 ohm is in parallel to both these 4 ohm and 8 ohm. Okay, so for that we have to redraw the circuit like this. So here I am having the resistances 4 ohm. Okay, so this 4 ohm, and here I have 4 ohm. Here I have a 8 ohm, and here I have a 8 ohm. Okay, and for this 4 ohm and 8 ohm, we have the 6 ohm in parallel. Okay, so for that we need to include these resistances. So this 4 ohm and 8 ohm have a resistance in parallel. So here I have 6 ohm. Okay, so this point is A, and this point is B. Okay, and now we need to find out the equivalent resistance. So whenever you redraw a circuit and whenever you find a parallel combination like this, okay, parallel combination like this, first of all you need to complete the parallel combination, complete the calculation for this parallel combination, and then you have to proceed with the next resistances. Okay, then only you will be able to solve the numerical problem correctly. So here you have 4 ohm and 8 ohm. So resistors in series, this 4 ohm and 8 ohm. So the total resistance is 12 ohm and this 6 ohm. So 12 ohm and 6 ohm are in parallel. Okay. So you have to find out the effective resistance of this branch. So 1 by Rp equal to 1 by 12 plus 1 by 6. I hope you can understand this because this thing, okay, this branch I am actually completing. This branch, okay. So this 4 ohm and 8 ohm are in series. So when I add both these resistances, I am getting 12 ohm. And for this 12 ohm, the 6 ohm is in parallel. So I have to complete this branch first. So 1 by Rp equal to 1 by 12 plus 1 by 6. So 1 by Rp is now equal to 1 plus 2, that is 3 by 12. So Rp is equal to 12 by 3, that is 4 ohm. Okay, that is 4 ohm. So now this branch, okay, now this branch is actually reduced to 4 ohm. Okay, so what you have to do now, you have to replace this 4 here and then you have to go for the next calculations. So now the circuit reduces to, here you will be having 4 ohm instead of all these 3 resistances. You will be having 4 ohm here. Okay, we will be having 4 ohm here. So that 4 ohm, this 4 ohm, and this 8 ohm, everything will be in series now. Okay, so I can redraw that circuit again for you. So here I am redrawing that. So here I am having 4 ohm, and this branch has been reduced to 4 ohm by our calculation. So here I have to use one more 4 ohm, and here I am having 8 ohm. Okay. Now all the resistance are in series. So what is the total resistance now? The total resistance R is equal to 4 plus 4 plus 8. That will be 16 ohm. Okay. That will be 16 ohm. And this option B is the right answer for this question. Do you all understand this? Students, anyone having any doubt?
No, sir, no doubt, sir.
Okay. I hope this is clear for everyone. So now we will be discussing our next problem. Okay. We will be discussing our next problem now quickly. A charged particle having drift velocity. Okay. Having drift velocity of 7.5 into 10 power minus 4 meter per second in an electric field. Of 3 into 10 power minus 10 volt per meter. Okay, 3 into 10 power minus 10 volt per meter has a mobility unit is actually meter squared per volt per second. Okay, of. So the options are 2.5 into 10 power 6. Option B, 2.5 into 10 power minus 6. Option C, 2.25 into 10 power minus 15. And option D, 2.25 into 10 power 15. So here we have been asked to find out the mobility. 10 power 15 here. So how we are going to solve this problem? The mobility you need to find out. So mobility formula we need to know. Mobility is represented by mu equal to drift velocity divided by electric field. Okay, drift velocity divided by electric field. This is the formula for finding out the mobility. And here the drift velocity is 7.5 into 10 power minus 4. Okay, divided by electric field. Electric field is 3 into 10 power minus 10. So what we have to do is we have to complete the calculation and then find out the value. So 7.5 by 3, what you will get? You will be getting 2.5 actually 2.5 into 10 power 6. Okay, so this 10 power minus 10, when it is taken to the numerator, it will be 10 power 6. 2.5 into 10 power 6 meter square per volt per second. So 2.5 into 10 power 6. So the correct option is this thing. Okay, option A, 2.5 into 10 power 6. This is option A. Okay, do you all understand this problem? Do you all understand this problem?
Yes, sir.
Yeah. Okay. So, do you all have any doubt in the concepts which we have discussed today in our class now? Today, do we have any doubts?
No, sir. No, sir.
Yeah. Yes. So, actually, you have one more concept. You have to understand, that is carbon resistors. Okay, carbon resistors. I think you know very well how to find out the value of the resistance in case of carbon resistors. For that, you have this trick to memorize that. Okay. So B means black, and this is brown, and red, orange, yellow. This is green, blue, violet, green, sorry, gray. Okay, gray and green. So that is BB Roy. So this is how you need to write down the order. Okay. One second. So you have a gray here. You have gray here. And you have white here. Okay. So for carbon resistors, you have to remember this order. Okay. So 0, 1, 2. So here 0, 1, 2, 3, 4, 5. This is 6, 7, 8, and 9. Okay. So you have to remember this order, and it will be useful for you to find out the resistance of a carbon resistor. Okay. For a carbon resistor, you have to remember this order, and then you have to find out the resistance value of the carbon resistor. And now, actually, we are running short of time, so let us keep it this much for this session. And thank you so much for joining the session. Let us continue our discussion on current electricity in our upcoming classes. So please do the revision regularly. This will help you to gain a good command over the concepts, and this will also be helpful for you to score very good marks in your NEET exam. So please do the revision regularly, students. And thank you so much for joining this session. Thank you.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you. Thank you.